All right, we have charts examples. Train A runs back and forth on an east-west section of railroad track. Train A's velocity, measured in meters per minute, is given by a differentiable function v of t, where time t is measured in minutes. Selected values for v of t are given in the table above. So we have t's and the velocity, meters per minute. A, find the average acceleration of train A over the interval 2 to 8. Well, average velocity, we use position. Average acceleration, we're going to use velocity. So we have v of 8 minus v of 2 over 8 minus 2. Well, v of 8 is negative 120, v of 2 is 100, and then 8 minus 2 is 6. And this is really y2 minus y1 over x2 minus x1. So we get negative 220 over 6, which is negative 110 over 3 meters per minute squared. Do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t with 5 to 8? Give a reason for your answer. So v of t is differentiable and continuous because, we're talking about velocity. So you can't go from 10 miles per hour to 20 miles per hour without hitting 15 miles per hour at some time in there. Since v of 5 is 40 and v of 8 is negative 120, by the intermediate value theorem, v of t must be negative 100 at some time within that interval. All right, let's look at letter C. At time t equals 2, train A's position is 300 meters east of the origin station. So it's on the east side, and the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. Use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at t equals 12. So we're using trapezoidal sum, so we need trapezoids. Let's take a look at the chart here. Let's get it back on the screen. Now we're starting at 300, and then we have 1, 2, 3 trapezoids. Now from 2 to 5 is 3 units, 5 to 8 is 3 units, and 8 to 12 is 4 units. So that's where we get this 3, 3, and 4. And then, the area of a trapezoid is 1/2 height times base 1 plus base 2. So then base 1 is 100, base 2 is 40. And then for the next one, base 1 is 40, base 2 is negative 120, and so on. Well, the total area is, the total area is negative 450. So we end up 150 meters on now the west side of origin station. A second train, train B, travels north from origin station. At time t, the velocity of train B is given by, so now this is the velocity. It's not given by a chart, but it's given by an equation. And at time t equals 2, the train is 400 meters north of the station. So they're given position at time t equals 2. Find the rate in meters per minute at which the distance between train A and train B is changing at time t equals 2. So if z is the distance between the two trains, then we're going to let x equal A's position and y be B's position. So then we have, if one's going north and the other one is on now really the west side, we have a right triangle. So this is z, this would be x, and then this would be the y. So x squared plus y squared equals z squared. Now we're trying to find the rate of change between the two. So we're going to take the derivative implicitly. We're going to take it with the derivative with respect to t. So we have tx dx dt, 2y dy dt, and then 2z dz dt. And we can divide everything by 2. So I'm not going to worry about the 2. So the next place we go is right here. So the velocity of B is of 2 is right here. Right here. This is actually what the dy dt. I think 125. Yeah. Because the position is 400. Anyway, we plug 2 in, and we get negative 20 plus 120 plus 25 when we plug 2 in here, and we get 125. Well, v of a at 2 was 100, and we were told that up here. There's the 100 right there. So we get that from the chart. Then x of 2 is 300 and y of 2 is 400. So they tell us there's train A is 300, train B is 400. And then just by the Pythagorean theorem, we know that position or the distance they're apart is actually 500. So now it's just plug and chug. So 100 times 300, 125 times 400, there's the 500. And when we solve for dz dt, what's the rate at which the distance is changing is 160 meters per minute. I'll scroll through the rubric here in case you want to take a look at this. There we go. All right, the second one, the function f is twice differentiable for x greater than 0 with f of 1 equals 15. So it's like they give us initial value. And the second derivative is 20. Values of f prime, the derivative of f, are given for selected values of x in the table above. A, write an equation for the line tangent to the graph of f at x equals 1. Use this line to approximate f of 1.4. Well, we need a point. We have the point right here, and we need a slope. The slope is 8. So y minus 15 equals 8 times x minus 1. We're going to plug in 1.4 for x, and we get 0.4. 8 times 0.4 is 3.2. Add 15, we get 18.2. So here's our first approximation of f of 1.4. So this is like a tour of different ways to approximate f of 1.4. Let's look at the next way. Letter B, use a midpoint Riemann sum with two subintervals of equal length and values from the table to approximate the integral of f prime of x dx. Use the approximation to estimate the value of f of 1.4. Show the computations that lead to your answer. So the integral from 1 to 1.4, from 1 all the way to the end, is, well, if we're going to use a midpoint Riemann sum, then we're going to go from 1 to 1.2 and use 10 as the y value. So from 1 to 1.2 is 0.2, and that's the base. So here's the base, and here's the height of the rectangle. And then 1.2 to 1.4 is 0.2 again, but now the height in the middle is 13. So we approximate the displacement as 14.6, but we're starting at 1. So the position at 1 was 15. The displacement was 14.6. So we're saying that the approximation for f of 1.4 now is 19.6. Use Euler's method starting at x equals 1 with two steps of equal size to approximate f of 1.4. Show the computations that lead to your answer. So I have that down here actually. I think I'll just close this for now. Letter C, we're starting with the point 115. And we know that if we're going to do two equal steps to go from 1 to 1.4, it's got to be 0.2 is the change in x. So we go from 1 to 1.2 to 1.4. So we know that the change in x is 0.2, but now we need the change in y. But we know that dy dx is equal to f prime of, is it f prime of t's this time, f prime of x's? It's actually f prime of x's in this case. So f prime of x. So dy, if we multiply both sides by dx, the change in y is equal to the derivative times the change in x. So now we know the change in y, it's 0.2, but we need to know the change in x, or the change in y. So the change in y is the derivative at 1, because we're at 1 right now, that's the x value, times 0.2. Well, f prime of 1, if you look at the chart, is 8. So 8 times 0.2, 1.6. That's the change in y, that's change. And so we add 1.6 to 15 and we get 16.6. Well, now we're at 1.2. So the change in y is the f prime of 1.2 times the change in x again. That's right here. And we get 12 times 0.2, which is 2.4. Add 2.4 to that. Now we have an approximation that is 19. So that's our third approximation of f of 1.4. Well, the fourth way is, well, Taylor polynomials approximate the values of functions. So write the second degree Taylor polynomial for f about x equals 1. Use the Taylor polynomial to approximate f of 1.4. So we have f of 1 is 15, the first derivative is 8, the second derivative is 20, and we have the second degree Taylor polynomial centered at 1. Well, I simplified it here. And then when we plug 1.4 in, this becomes 0.4, this becomes 0.4. And that's right here. So we have 15 plus 3.2 plus, it ends up being 1.6. So our final approximation for f of 1.4 is 19.8. Here is the rubric for it. I'll scroll through if you want to take a look. There we go. On this one, we have let u equal x over 3. If this was 16, we would let u equal x over 4 and so on. And that allows us to multiply both sides by 3. So the derivative is 3 du, and the derivative of x is just 1 dx. Well, now dx is going to be replaced with 3 du. And if we plug 3u in for x squared, we get 9u squared. So we have 9u squared plus 9. There's the 9u squared plus 9. We can factor out a 9. That gives 3/9. That's 1/3. Now this is the derivative of inverse tangent. So inverse tangent of u plus c, and we replace u with x over 3, and there's the final answer for that one. Find the intervals on which f of x is increasing and decreasing if f of x equals this function. So we're going to take the derivative, set it equal to 0. We get negative 5/3 and negative 1. And then we test in between. Now you plug negative 2 into the derivative. So negative 6 plus 5, that's a negative. That's a negative. Negative 2 plus 1, that's also negative. So this function is increasing from negative infinity to negative 5/3, decreasing from negative 5/3 to negative 1, and then increasing again. Now, we don't have to throw out everything we've ever learned about an x to the third. I mean, x to the thirds typically look like this right here. So what we're trying to find is that maximum and minimum value. So there's the maximum, there's the minimum, and then we finally write the answer as increasing and decreasing.